All right, so I need to teach Slack, right? Both of you already have your CUW.edu email, or you don't have a CUW.edu email?
Yes.
You do. All right, so what you'll do is, everybody else in here, I think, everybody else is on Slack already? All right, so you'll go to cuwcs.slack.com. So CUW Computer Science, cuwcs.slack.com. And then down here it says if you have a cuw.edu email address, create an account. So do that.
Do you actually have to do that?
Huh? It won't let you create an account unless you have a cuw.edu address. So if you don't have that, I can invite you. So you're not out of luck. This is the way you can directly create one. And then once you do that, you can do it through the web. You can get the Slack app for your phone. So Slack looks like this. I get it on my phone, so the things come in like texts on there. And then we have a 548 channel in here. So if you haven't already done so, everybody should join this 548 channel on Slack. So it'll dump you into general here. Yeah, see, Maddie's already in there.
Two, actually. One of them's kind of funny.
Which one?
A screenshot.
A who?
A screenshot, I sent you.
Oh.
One of your messages.
Oh, down here. Shouldn't open that on video because there could be stuff in that conversation. I'm on video. All right, so does that make sense?
Yep.
Yeah, so it's a chat thing, but it's a good way of asking questions for homework and stuff. Sometimes, I get them quickly, so she chats with me on Slack all the time. It really just kind of depends on if I'm at school. I tend to use Slack more or WhatsApp because my cell phone, this is something weird. I used to have no problem with voice over IP working for text messages on my Note 9. Well, this is the Note 10, and now I basically have a 5% chance of when I try to send a text message over Wi-Fi that it works.
What?
Text messages work just fine when I'm on a normal cellular signal. But here on campus with AT&T, you have like no signal.
That's insane. That's awful.
Yeah.
Especially in here.
So I'm guessing it must be like a software thing because this is not the way it used to work with my exact same carrier, Samsung Note 9. So it's probably a weird thing with the new phone or possibly something provisioning. In fact, it might even just make sense. As much as I use it, I should just call AT&T and probably get nowhere, but you never know. But it is weird. I can't get text messages when I'm on campus very regularly. They'll eventually come in, like the moons align, and it eventually works, but I can get Slack messages anywhere. So anytime you send me Slack, it'll work. Oh, did I get Diet Mountain Dew?
That's the only thing I have.
Oh, I love Diet Mountain Dew. It's my favorite. 8 for the day.
Isn't that $40?
Huh?
$40 for a semester only?
$40 for the normal one, which can get you soda. Well, it can get for the semester. Yeah.
How do they know what next semester they do?
I don't know. I don't know if it's a new sticker or
What's
they put a
the-
sticker on the bottom because I got the premium one. It's the same cup.
They didn't even-
So regular. Yeah, they don't care. I think they're just used to seeing people with this.
What is it, like a cup something or other that's going on?
Yeah, Sodexo has a thing. I've been telling them to do it for years. It's like this quench cup. So I got the premium one. So I paid $60, and for the semester I can get any liquid that is at any of the cafeteria stuff out of like the machines, like juice, soda, whatever. I can get coffee. I can get Starbucks coffee, Starbucks iced coffee, Starbucks hot tea, the Teavana hot tea, and Teavana iced tea. I can't get lattes and stuff, but I can.
Okay. That's for the entire school.
For the semester.
Put coffee in there, though?
Yeah, it actually works great. It's like double insulated. Like I had coffee in here the other day, and it was still very hot several hours later.
That's interesting.
Yeah. So It's you're late. Like 2 hours late. All right. Well, you'll have to watch the videos because I'm not going back. All right. So, okay. So that's Slack. Okay. So let's go back in here. So we talked about the job of the compiler, right? So takes our high-level language that humans like writing stuff in, converts it for a targeted architecture and for a targeted operating system into low-level code, which is a one-to-one relationship with the CPU, which will end up looking something like this. This would be the output of a compiler that took a high-level language, probably something like C or C++, and turned it into x86 assembly targeted for the Linux kernel, the Linux API. All right, so those are the two pieces. Whose assembly language, whose low-level language, and what operating system should it work with? Because you could take this identical processor, let's just say this is a Core i5 processor, and you can stick it into a Mac, and it will produce different output because the system calls are different. The way it handles those things, maybe the syswrite system call takes more or less inputs, that kind of thing. It's probably not even called syswrite on a different one of the operating systems. It's called maybe, like Windows has these big long names for their system calls, but it's going to do something like this-ish. All right. Okay, so now let's I'm going to go pretty quick through the scheme intro because you guys are grad students. You can learn stuff real quick. So I'm not going to spend too much time on it, but scheme is really simple, but that way we can start doing some stuff as I go through some exercises here. All right, so the language we're going to use in here for representing for solving some of our problems, for learning some of our things, is going to be this language called Scheme. Scheme is a superset of Lisp. And by superset, it means it's backwards compatible with Lisp, but it adds some more stuff in it. We've already talked about this idea of superset and things like that with the processors and those architectures. I'll put in here that it's something known as a functional language. Now, I'll put a link up for this, but if you go to, huh?
Did you say you put your slides up?
I thought I did. Are you lying? Collaborate. Yeah. The link should be on the left. The Blackboard. I don't know, slides? Here, just for now, I'll put it in Slack. There. All right, so it's a functional programming language. The tool we're going to use to get this is a tool called Dr. Racket. Here's Dr. Racket. I'll put that on Slack. All right, so just go to download. It'll choose which thing. Notice this x86. This is x86 64-bit architecture. So there's an example of when you see that x86 thing. All right, so this effectively says 64-bit Intel architecture. That's what those characters mean. So download this for your platform. It supports Mac, Unix, Windows, Linux, blah, blah, blah. So whatever you have, it supports. You got to be using something pretty strange if it won't. All right, so once you have Dr. Racket installed, it's going to look something like this. All right, so that's what it'll end up looking like. So one of the reasons that we use Scheme in general in various language classes is because Scheme is a very small language. So it allows us to focus on the problems that we're trying to solve rather than the language itself. So this course is not going to be about learning Scheme, which is why I'm not going to spend tons and tons and tons of time giving you the Scheme intro, but we're going to fly through the Scheme intro here pretty quick, and then you'll just have to kind of play catch up as we go. So I'm going to show you the Scheme primitives. So Scheme primitives. We have something called car, cooter, cons, append. I'll put define before this. Define. Let's leave it at that for right now. We'll call those the Scheme primitives. There is a Scheme reference somewhere, like scheme.org, I think. Yeah, this will probably do something. Cond is not one of the primitives, but we'll talk about here in a second. But yes, you're right. There's the language reference. Okay, so just throw a quick slide up here. The whole how do humans solve problems slide. If you've had programming classes with me, we use our memory, ask questions, repetition. All right. And then I usually have a slide off of this called the mapping. 100% of programming languages have a mapping for these things. Memory is usually accomplished through variables. In Scheme, that is through the define function. Asking questions is done through conditionals. In Scheme, this is the if or the cond functions. And repetition is typically done through loops, but Scheme doesn't officially support loops. There is a function for it, but you're not allowed to use it. So this is accomplished in Scheme through Lambda, calculus, and recursion. And we'll talk about those things. All right. So bottom line is, any programming language you're ever introduced to, it will have facilities for memory, asking questions, and repetition. If you can figure out how to do those three things with it, you can already solve a whole bunch of problems with that language. Okay, so I'm going to show you how to do those three things with Scheme, and then you should be able to solve any problem. Okay, so let's just go in here. Scheme is a list-based language. As opposed to like Java, which is string-based. So list-based language, a list is an open parenthesis. Let's go this way. Open parenthesis, func name, param 0, param 1, dot, 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 param n. All right, so this is how functional languages work. It's an open parenthesis with the function name followed by the parameters you want to send it. All right. Now, if you want to create your own list and you don't want it to try to call this function called funcName, you put a little quote before it, and now you can create lists like 1, 2, 3, 4. All right. If you don't put the quote before it and you say 1, 2, 3, 4, it's going to look for a function called 1 and try to apply it to the inputs 2, 3, and 4. Okay. So I'll go ahead and create a couple of variables. I'll define a variable called A. We'll set this equal to the list 1, 2, 3. Okay, so this is open parenthesis. There's no quote before this. So this is the defined function. And the defined function takes two inputs, a variable name and its value. Name value pairs. That's what variables are. That's how you do it in Scheme. All right. So if I hit run here, it runs it through the interpreter. If I type A, because you can directly interact with the interpreter down here, it shows me that list. All right. So now we know how to define variables. All right. So now we need to know how to manipulate things. That's where the cars and the coulders come from. All right. So these guys are a ton of fun. So this is variables. Car returns the first element of a list. That's what car does. So the car of A will give me the very first element in A, which is a 1. Make sense? Now, don't confuse elements with lists. So for instance, I can say define B to be the list containing the list 1, 2, 3. So now B is a variable name whose value is a list containing two elements. The first element is a list containing two elements. The second element is an integer literal. So the car of A is still 1. What will the car of B be? Car of B be the list 1, 2. If I want to say the car of B, that will give me the 1. The car of B is the list 1, 2. The car of that is the value 1, the first element of that list. There is some syntactic sugar you can do, but you never have to use it. You could say I want the car of B, which will give you the 1. All right, so until you get used to Scheme, I wouldn't use these special things. I just do everything with cars and cooters until you become comfortable enough with it that it becomes annoying. And then you'll say, okay, I actually only need to go one level in, so I'll just ask for the cadr, CADR or something like that. All right, so that's what car does. Gives you the first element of a list. So cars take one parameter. The name of the function is car. Its single input must be a list. So far, so good? All right. Cooter returns the rest of a list other than the first element as a list. So if car gives you the first element of the list, cooter gives you the rest of the list as a list. Everything except the car. So the cooter of B, if the car of B is the list 1, 2, the cooter of B will be what? The list 3. Oh, Ninja. Cooters always return a list. Always, 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 always return a list. Now, if I had changed B to be, if B was a 2 list, where the first element was a 2 list and the second element was a 1 list, get that quote out of there. And then I said, give me the cooter of B. It will give me everything but the car as a list. So this will give me the list containing the list 3. Or the cadr of B will give me the car of the cooter, which is the list 3. Or I could say the cadr of B, which will give me just the 3. And CAADR is like saying, give me the car of the car of the cooter of B. That's what it's shorthand for.
What is a comment?
I don't know. Maybe semicolon? Looks right. Yep. All right, so we're good with cars and cooters? Easy peasy? Okay. Now, for the moment, right now, you're supposed to be thinking in your head, okay, what the heck would I ever use these for? And that's okay. We will see very shortly. All right, cons. This is a way of constructing lists. So cons allows us to construct a list. So I can cons a value like a 5 onto A. And this will give me the list 5, 1, 2, 3. The second element of a cons must be a list. So I can say I want a cons 1 onto the cons of 2, onto the cons of 3, onto the empty list. This cons will boil down to 3 being constructed onto the empty list, give me a list of 3. This will give me the list 2, 3. This will give me the list 1, 2, 3. Make sense? The second parameter must be a list. So I can't say cons 1, 2, because it says the second argument must be a list. Oh, one thing I should point out, I have already done it in mine, but when you first get Dr. Scheme installed, or Dr. Racket, it used to be called Dr. Scheme, click on language, click on choose language, and select advanced student under teaching languages. It might be beginning student by default. Choose advanced student. That will make a difference for the more advanced things. Cars and cooters are super simple, so nothing would have broken at this point so far for you. So just choose advanced student there. You only have to do it once and then it'll be stuck. Okay, so we're good with cons. Cons constructs lists. All right, then we have this guy called append. Append glues lists together. So I can append A and B, and that gives me a new list with the contents of A as the beginning and the contents of B following it. So it doesn't give me a list with 2 sublists in it. It takes the contents of the first list and the contents of the second list and gives you one list with all that stuff in it. Make sense? But append requires both parameters to be lists. So far, so good? All right. So now, let's learn how to ask a question. I can say if less than, let's see, order of operations for this. Let's do, if the car of A is less than 5, that's what that asks right there. If the car of A is less than 5, then, and actually I'm going to write it up here. That way we can experiment with it. If the car of A is less than 5, then we want to output, I don't know, we'll output a 10. Otherwise, we'll output a 15. So the car of A is what? A 1? Is 1 less than 5? Yes, that's true. So the result will be a 10. But if I change that to greater than, car of A is 1. Is 1 greater than 5? It is not. It will boil down to the false statement, which is 15. Make sense? If. Function name is if. First parameter is a Boolean expression. What's a Boolean expression? Any expression that boils down to a single value of true or false. Next thing is true expression. Next thing is false expression. Name of the function is if. This is what gets tested, the Boolean expression. If that guy boils down to true, the true expression fires. If that guy boils down to false, the false expression fires. Make sense? All right. We also have a thing called a cond, which is similar to a switch statement in some programming languages you might have had. So parameter is, so it goes like this. Cond Boolean expression true expression dot Boolean expression true expression, and then at the end there's an else expression. And I'll show you this one as an example. It's easier to follow with an example. It allows you to ask multiple questions, only firing on the thing that made sense. All right, so I can say cond. Now, one thing you're going to want to do with Scheme, and if you use the area up here, this is kind of like your text editor, is put things on multiple lines because things are going to get pretty scary once they start going too far over. So when you kick it down, it automatically indents it for you. So I'm going to do a cond. We're going to say if the car, greater than car A 5, then we're going to say 10 equal to car A 5, we'll say 15, else we'll say 20. So this says if the car of A is greater than 5, boil down to 10. The car of A is equal to 5, boil down to 15. Otherwise, boil down to 20. So right now the car of A is 1. Is 1 greater than 5? Nope. Is 1 equal to 5? Nope. So it should boil down to a 20. The 15 is for my if statement up here. So it did boil down to 20. If I change this guy to a 5, now it's equal to 5. It should boil down to a 15 here. Now if I make it a 6, it'll boil down to a 10 because 6 is greater than 5. Make sense? All right. So now you know how to ask questions in Scheme. So you know this guy. You've learned 2/3 of this language. Last thing, repetition. let's talk about lambda expressions. All right, so first of all, we look at that and we say, okay, that sounds difficult, right? Kind of seems intimidating. I can see the deer in the headlight look going on over here, right? Okay. So what is the definition of a lambda expression? Anybody who has had Scheme before know the answer to this? Unnamed function. Good. And these things exist in every single programming language. So a lambda expression is an unnamed function. We typically give functions names when we define them. So for instance, if we're working with a language like Java, let's jump over to Eclipse here for a second. So right here we have a method called main. If I take that off, now I have an unnamed method, an unnamed function. So what is a function? Function is a collection of parameters, inputs, and then the body. What does it do? What happens when we name it? It's like a variable name. We have a variable named main that is equal to this lambda expression. It's equal to this function. Variables can have normal values. We can have an integer, we can have a char, whatever, but a variable can also be equal to a function. It's worked this way in any programming language you've used up to this point. You just never thought that you were defining a variable. You always thought that functions and variables were different animals. They were different things, right? They're not. You're associating a value with a name. The name is main, the value is a function. All right? So lambdas are unnamed functions. If we want to name it, we have to associate it with a variable. How do we associate things with variables in Scheme? With define. So I can say something like define my func to be a lambda expression that takes maybe two parameters, a and b, and maybe this guy spits out a plus b. Okay? Now our output isn't any different than it was a second ago. Why? I just wrote a whole bunch of really awesome looking code. Why is my output no different than it was a second ago? Just defined my function. I haven't called my function. So I have a function now called my func. And what does my func do? My func takes in two parameters and boils down to those two parameters added together. So if I were to call upon my func, how do we call a function? Well, we use an opening parenthesis. The function name, if I pass it a 1 and a 4, what's 1 plus 4? It's a 5. If I then call my func again, and I passed it a 21 and a 76, it's going to give me a 97. I have a function. That is my unnamed function right there. A lambda expression is a function that takes 0 or more parameters, this guy takes 2, and does something with them. Make sense? All right, so now to finish the loop here, pun intended, I mentioned that we do loops with recursion, okay? And Alexis told us that recursion is when a function calls itself from within itself. So we're going to go ahead and almost always when we teach recursion, we talk about recursion in terms of the factorial problem. So remember this from math, 4 factorial? So 4 factorial is 4 times 3 times 2 times 1, okay, which is 24. Now, what's 3 factorial? 3 times 2 times 1? What's 2 factorial? 2 times 1? And what's 1 factorial? 1. So 4 factorial is actually equal to 4 times 3 factorial. It's a function defined in terms of itself. 4 factorial is equal to the number 4 times the factorial of 3. 3 factorial is equal to the number 3 times the factorial of 2. 2 factorial is equal to 2 times the factorial of 1. 1 factorial is 1. So when 1 factorial finishes, this guy can then get his answer. Now this guy can now get his answer. Now this guy can now get his answer. And now this guy can get his answer. Make sense? That's how recursion works, and that's how we will accomplish our loops. So if we wanted to define factorial. Factorial is a function that takes a single parameter, right? It takes a single parameter. Actually, let me kick it down this way. And if that parameter is equal to 1, it boils down to 1. If equal n1, boil down to 1. Otherwise, what do? Otherwise, I'm going to return times n and whatever is returned for the factorial of minus n1. Here, let me spread this out a little bit more. It might be easier to read this way. So I'm defining a variable. The variable's name is factorial. It's going to be a function, so we're going to create a lambda expression. This function takes one parameter. I named it n, you can call it whatever you want. Then I'm asking a question. If it's equal to 1, I'm done. Boil down to 1. No more recursive calls. Otherwise, multiply. Otherwise, I should boil down to or return n times the factorial of n minus 1. So if n was 4, this guy's going to boil down to 4 times the factorial of 3. This guy was 3, it's going to boil down to 3 times the factorial of 2. If it was 2, it's going to boil down to 2 times the factorial of 1. This guy was 1, it's going to boil down to 1. Make sense? So now, I can say factorial of 4